out briefly what's happening in our atmosphere. Here's sun putting out sunlight. And here's the Earth, drawn completely to scale. Here's you, also drawn to scale. And so the sun is constantly bombarding the Earth. It's where we get our energy from, right? But most of the light that's coming in, there's a distribution, right? But most of the light that is coming in is UV and visible. Okay, that's certainly primarily the most energy we get from the sun is this UV visible light. Now, the Earth would just keep heating up forever unless we were able to cool ourselves. It turns out Earth does not radiate on its own UV or visible light. Well, not much of it. What it radiates is IR light, and IR light, of course, is longer wavelength. Okay, but this is a very basic picture of our thermal equilibrium as a planet. Obviously, the Earth is rotating, so at night, we're not getting that UV vis. We're still radiating away IR, and we cool down, right? But overall, there's sort of this equilibrium, energy in, energy out. But what happens, right? All this UV is allowed to get through. All this IR is allowed to get out. Why is the IR allowed to get out? Well, because there's nitrogen and oxygen here. And that's not getting in the way of this IR light. Why? Because those things don't absorb IR light. So the IR doesn't really interact with any of these homonuclear diatomics. And so the energy escapes and we maintain our constant temperature, right? So this is our thermal equilibrium. This is necessary. But what happens if we add non-homonuclear or non-diatomics to the atmosphere? And the most well-known one, of course, is, like we talked about back here, CO2. CO2 has a dynamic dipole. And so if we add CO2 to our atmosphere, well, now it is interacting with this IR light. And it's interacting because it has this dynamic dipole. It doesn't have a permanent one, right? No permanent dipole. That matters for rotational motion. But for vibrational motion in IR, there is a dynamic dipole because the unequal charge distribution has a time dependence here when this is vibrating back and forth and this bond's elongating, right? The charge around carbon is being sloshed around unevenly. And so there is a dynamic dipole. That electron density overlap is changing not symmetrically. So CO2 absorbs IR as we add it to our atmosphere, right? This is you. This is you doing bad stuff and adding CO2 from our atmosphere out of the back of your car or something. It's floating up here into our atmosphere. Now, when the Earth tries to sweat and get rid of this light, right? You're pumping CO2 into the atmosphere from fossil fuel combustion, or maybe you're just procreating and making higher populations, or maybe you're cutting down forests that are supposed to turn CO2 into oxygen. All of these things add these IR-absorbing molecules to the atmosphere. And now the energy that Earth is trying to radiate away and cool itself down is absorbed and kept in our local environment. Okay? Sometime later, the CO2 will relax and maybe spit out this IR, but it's not guaranteed that it's going to spit it out to space. Right? Much of the time, it's going to re-emit it down towards the Earth where it gets reabsorbed. Right? So some of this emitted radiation by CO2 goes back into the Earth. And so the net effect is it's the same energy that's coming in, but there's less energy going out. Okay? And so that's a higher overall temperature overall. The Earth keeps heating up. That's our global warming that's affecting our climate. And now, this is you.